pleasant presentation. Okay, so, okay, I'm going to speak. You see that's a joint work with Marie-Françoise and Marta Garcia-Huidobro, which is supposed to appear in Calculus of Variation this year. Okay, and my problem is the following. I consider first, omega is a bounded C2 domain. I assume now that P is a parameter bigger than 1, Q is between 1 and 2, and M is positive. And I'm interested in studying the boundary behavior of positive solution of the equation that I note L PQM of U, and this is minus Laplacian of U plus U to the P minus M grad U to the Q is 0. Okay, so this equation has three aspects. There is a diffusion, of course, coming from the Laplacian. There is absorption coming from U to the P, and there is the forcing term, the source, coming from M grad U to the Q. So there is a competition between U to the P and grad U to the Q. And I'm interested in two problems, essentially the existence of solution with boundary measure data and the description of the solution with a boundary isolated singularity. Now, existence of critical exponent both in P and in Q, and of critical values for M. This makes the problem rather complicated. So it's not the good one. Okay. Now, first, notice that if Q is 2P over P plus 1, this is a particular value. The equation is invariant under scaling transformation. The scaling transformation is TL, which is defined by TL of U applied to X is L to the 2 over P minus 1 U of Lx. So actually, when Q is less than 2P over P plus 1, the absorption term is dominant and the behaviors of singular solution is modeled by the Emden-Fowler equation, which is minus Laplacian of U plus U to the P is 0. Now, contrary, if Q is 2P over P plus 1, the source term is dominant and the behavior of singular solution is modeled by the aconal type equation. There is no more diffusion. And another equation which plays a role in modeling the equation, the solution, is a Riccati equation minus Laplacian of U minus M grad U to the Q is 0. And in the critical case, Q is 2P over P plus 1, the value of M becomes fundamental. And now what is important to notice for construction of solution, that the Emden-Fowler equation and respectively the Riccati equation is a sub-solution resp a super solution for the initial equation 1,1. Okay, now I present the space of test function for analyzing the boundary value problem, which is a classical one, which is I've been used many, many times since 30 years. This is I call the space X of omega, which is a set of function Z in C1 of omega bar, vanishing on the boundary, and such that the Laplacian belongs to L infinity of omega. This is a standard, just this is natural, just to see the role of the space, and weak solutions are defined formally via green formula with test function in X of omega. Now, first question is about boundary singularities. Okay, I agree. I assume now that 0 is in d omega. And I'm interested in the problem, which is the starting point for boundary singularity. That means you have a solution of the equation L PQM of U is 0 in omega, which vanish on the boundary except one point. Now, what I have that the following. I have a theorem of removability of singularity. If P is bigger or equal to n plus 1 over n minus 1, and M is positive, you take any C2 solution of this equation here, then you know the result is, okay, I'm going to make the assumption after. Then U belongs to L1 intercept with LP rho, and grad U belongs to LQ rho. And the equation is satisfied for all x in omega if one of the following condition holds. In the case P equal n plus 1 over n minus 1, and Q is between 1 and n plus 1 over n. Or if P is bigger than n plus 1 over n minus 1, and for any Q less or equal to 2P over P plus 1. So you see, this is just the fact that the equation is satisfied. It does not give any estimate of the behavior of the solution near the boundary, okay? It's just an equation which is satisfied in this sense, some sense of weak sense. Now we can improve this result. Now, if we assume the following, either I recall what is I, what is P is n plus 1 over n minus 1, and Q is between 1 and n plus 1 over n. Or P is bigger than n plus 1 over n minus 1, and Q is less than 2P over P plus 1. Or P, again, is bigger than n plus 1 over n minus 1, and Q is equal to 2P over P minus 1. So this is a critical value. And in that case, we need M to be smaller or equal to some value here, M star, which is this one. Then in that case, U is 0. So I recall this equation. If we have, okay, the critical value is always at n plus 1 over n minus 1 for P. Now the problem is, what is the role of Q? The role of Q, in some sense, here or here, okay? And we have a solution which is satisfied without seeing, actually, that means that the solution does not see the singularity, but that may be something. And now, if we improve the estimate, the conditions, assumption, then this one and this one, or this one and this one, or P bigger than, this is most interesting, is this one, P bigger than n plus 1 over n minus 1, Q is 2P over P plus 1, and M is less than this specific value here. Then the conclusion is that U is 0. And in the case I, you see there exists solution which satisfies the equation. The equation is this one here. There exists solution which satisfies this equation, which they have a singularity which is concentrated at 0, but this singularity is weak, cannot be detected in the sense of distribution. This is a standard phenomenon which occurs for the equation minus Laplacian of U equal U to the P in omega for U vanishing on the boundary, in the case where P is between n plus 1 over n minus 1 and n plus 1 over n minus 3. These are results that I prove with Marie-Françoise and Augusto Pons. Okay, this is something which is classical. That means the singularity are not in the sense of distribution, but they exist. Now the idea of proof. Okay, first thing, to get an a priori estimate. The a priori estimate is the following. If M is positive and Q is between 1 and the minimum of P and 2, then any positive solutions of the equation, that means that it satisfies the equation in omega and vanish except at 0. Then we have this a priori estimate. U of x is bounded by C1 max of m to the 1 over p minus q x to the minus q over p minus q, okay, x to the 2 over p minus 1. So here you have this type of estimate. This estimate is an agonal type estimate. And this is an estimate coming from the Emden-Fowler type estimate, okay? A consequence, since q is less than 2, that you have an estimate also of the gradient. The gradient is going to be bounded by essentially the derivative of this estimate. Okay, that means that the max of x to the minus p over p minus q and x to the minus p plus 1 over p minus 1. So this is the first thing. Then the second idea is to set u is v to the b, with b is between 0 and 1. Okay. Then in that case, there is a new equation, the equation 115, minus Laplacian of v minus b minus 1 grad v square over v plus 1 over b v to the p minus 1 b plus 1 minus m bq minus 1 v to the b minus 1 q minus 1 grad v to the q. This is the new term. So what is good here? This is a good term in some sense. And this is something which has to be controlled. This one too also, but the main difficulty is this one. So how we control it? Well, we control it, this is called the bad term, the last term, by Hölder estimate. I Hölder estimate, well, epsilon is a free parameter. So then I have this estimate that the v to the b minus 1 q minus 1 grad v to the q is bounded by some here term grad v square over v plus 2 minus q 2 times epsilon to the 2 over 2 minus q times v to this power. Okay. So this is now what we get. We get this new equation here. So now what I have to notice now in this equation, I have minus Laplacian of v plus this not pleasant term here, plus this one, which is always a good one, because this is I'm going to choose it bigger than 1. And I have the term here, which is remaining, which has this power. And notice also that this power, this exponent here, is truly independent of b. And if we want this exponent here, this power, to be smaller or equal to this one, that means if 2b minus 1q minus 2b minus 1 over 2 minus q is less than p minus 1b plus 1, this is equivalent to q is less or equal to 2p over p plus 1. So this is why this is fundamental, because we want this term to be dominant. Now we choose exactly b is 2 over n minus 1 p minus 1. So this gives exactly the term that we have, p minus 1b plus 1. Remember, this is this exponent here. So this exponent is equal to n plus 1 over n minus 1. This is a removability threshold for boundary singularity. Okay? Now, if I assume p is bigger than n plus 1 than minus 1 and q is less than 2p over p minus 1, I make this choice of epsilon and it transforms this equation in this one. It's a very simple one. Okay? This is a very simple one, and I use the result of Guimirin and myself, and the consequence is that v is bounded. Now we use a suitable choice of test function, make a reflection through the boundary, use Serin's result, and we have the consequence that the equation is satisfied. Okay. Now, if p is bigger than n plus 1 over n minus 1 and q is 2p over p plus 1, we have the same choice of b, but a sharper choice of epsilon, and in order to take care of m. And now, in the case p is n plus 1 over n minus 1 and q is less than n plus 1 over n. So in that case, We cannot use directly this method, but we are going to use this estimate 113. This is a precise estimate of U, okay, of bounded by this estimate. Up to now, you notice that I have not used the a priori estimate. Now I use here the a priori estimate. I use this a priori estimate that U of X is bounded by the max of constant times X to the minus Q over P minus Q and 2x to the 2 over P minus 1, minus 2 over P minus 1. I improve this allows to improve the estimate on the gradient, and then by iteration, we derive the boundedness of U, and the end is easy. Okay, so this is a proof of this removability result. Now, this removability result can be extended to more general boundary singular set with a parameter. So I just gave you like this because it's not really easy to analyze. I assume that P is bigger than n plus 1 over n minus 1. Now I take a free parameter R between n plus 1 over n minus 1 and P. Now, if one of the following conditions is satisfied, either Q is 2P over P plus 1 and M is smaller than M, I call it M double star of R. Remember that I've already used M star, which was important in the case Q equal 2P over P plus 1. So if M is smaller than M double star of R, which is defined by this expression, R being this free parameter, or if Q is between 1 and 2P over P plus 1 and R is less or equal to 3, and M is arbitrary, then the result is the following, that if K is a compact subset of d omega with a capacity, the Bessel capacity 2 over R prime of K is 0, then any solution of this equation LPQM of U is 0 in omega, which vanish on d omega minus K, is actually identically 0. Okay, this is an extension of the result. Of course, there is this parameter. Probably this result can be improved, but up to what level, I don't know. Okay, these are the result I have about singularity. Now, I would like now to study a little the problem with measure boundary data. With measure boundary data, the problem is the following. I consider this equation, LPQM of U is 0 in omega, with a boundary value U equal to some measure mu on d omega. What is the solution? Of course, a solution, in order to give meaning to the solution, I want U to be in L1 of omega. This is because of the set of test function. Okay, U in L1 of omega intersect with LP rho. Rho, remember, is the distance boundary. LP rho of omega and grad U in LQ rho of omega. And I assume that for any zeta in the space of test function x of omega, I have integral of omega of minus U Laplacian of zeta plus UP minus M grad UQ. Zeta is minus integral of the boundary of d zeta over d nu integrated with respect to the measure d mu. So here U is delta zeta is in infinity, U is in LQ, so it has a meaning. Now zeta vanishes on the boundary and it is C1, so zeta is bounded by C times rho, and U is in LP rho, and grad UQ is in grad U is in LQ rho, so see, everything has a meaning. Now to this problem, I am going to associate two problems. I'm going to associate two problems with measured data. Minus Laplacian of V plus Vp minus 1 V is 0 in omega, and V is with mu on d omega, and minus Laplacian of W plus M grad W to the Q is 0 in omega, and W is mu on d omega. So I associate the two problems here, which are going to play a very important role. Now, for the first problem, this is an Untitled equation with measure boundary data. Well, we have studied a lot. We have studied this with Moshe Marcus a very long time, and we have proved a complete result. We are not alone because on the other side, people like Dinkin, Kuznetsov also study this problem by probabilistic method and with a shorter range of exponent p. Okay, but essentially we prove that if, in order to have a solution to the Emden-Fowler equation with measure boundary data mu, then we need this one. That means a measure must be absolutely continuous with respect to the capacity 2 over pp prime, which means that if the capacity C 2 over pp prime of a Borel set E is 0, this implies that the measure of E, absolute value of E, is equal to 0. Now for the problem of the Riccati equation. For the Riccati equation with boundary data mu, so this has been studied by Marie-Françoise Wang, Guyen, and myself. And we prove that a solution of this Riccati equation with measure mu boundary data mu exists if for all Borel set E, a mu absolute value of mu of E is bounded by C times the capacity, which is going to be the capacity C2 minus QQ Q prime. So first here, it's just a question of the measure being absolutely continuous with respect to the capacity. Here it says that the measure is Lipschitz continuous with respect to the capacity. So this is a different point. Okay, with these two things, these two important results, we have the following result. We assume that P is bigger than 1. Q is between 1 and 2, and mu is a non-negative random measure on d omega. And we assume that it satisfies this estimate, that mu of E is bounded by C times the minimum of the capacity C2 minus QQ prime of E and the capacity C2 over P prime of T for all Borel set in d omega. Then there exists a C0 positive, such that for any C less or equal to C0, there exists a non-negative weak solution of the problem. That means LPQ of M is 0 in omega with mu, with C mu as a boundary value. Furthermore, the boundary trace of U is the measure C mu. And actually, the fact that the boundary trace of U is C mu will play an important role. Now, we also notice that if P is between 1 and n plus 1 over n minus 1, so there is no condition involving this capacity here. Okay, because only the empty set has 0 capacity. Now, also, if Q is between 1 and n plus 1 over n, there is no condition involving this capacity here. Okay, this is a remark which is notice it's important. So we have these two capacities. So what is the link? Well, first the scheme of the proof. The scheme is very easy in some sense. The idea I use, remember the solution, V mu is a solution of Emden-Fowler equation with boundary data mu. This is a self-solution for the equation for this operator here. And it is a solution, the solution of V mu of the Emden-Fowler equation with mu boundary data is actually smaller than any solution W mu of the equation, which is a Riccati equation, positive, of course, positive solution, with the same mu boundary data. And the W mu here is a super solution for this equation. So we have a sub-solution, a super solution, both positive. So they are defined in open set omega. So this is a standard that, well, by approximation, that you have a solution in between. That means there is a u mu which satisfies LPQ of u mu is 0 in omega. What is the consequence of this? Well, the consequence here, we are going to use the notion of trace. Notion of trace, because we have no idea, of course, what is the boundary value of u mu. But we have this. The fact that W mu satisfies the Riccati equation with mu as boundary data implies that the limit when rho of x of W mu d zeta ds, okay, this is the same here at the limit of, it is going to be, the limit here is going to be integral of z d mu. I've forgotten to write, but when you look at the equation, the solution W mu with boundary data mu, then that means that the solution has boundary trace mu in the sense that for any function z in C of bar omega, then this here is integral of z d mu on d omega. So this is the same as the limit when delta goes to 0 of integral of rho of x is delta of v mu z ds. It's the same. So by the sandwich theorem, then this implies between, because u is between v and w, that the limit of rho of x when delta goes to 0 of integral of rho of x delta of u mu zeta is integral of z d mu. So at least in this trace, in this sense of trace, we have the fact that the boundary is achieved. But this is not enough. We need now to have estimate of up and grad uq. Now, what are the estimates that we have on v mu? On v mu, we have this estimate. V mu is bounded by the Poisson potential of mu, which is again bounded by the W mu. And this is a result which is obtained that actually W mu, here, this is a result that we have with Marie-Françoise, Laurent, and Veron, that W mu is bounded by C times the Poisson potential of the motion. Second estimate, this is just by maximum. This part is just by maximum principle. This one is more tricky. Now, second estimate that, of course, at 0, okay, this is less or equal to v mu, is less or equal to u mu, is less or equal to w mu. This is just the construction of solution. Now, I'm going to associate a new equation here. This is this one. I associate to the problem the equation with a forcing term, which is, I look at this equation minus delta zeta, minus delta z, minus zp. So this is not the Emden-Fowler equation, it's called the Lane-Emden equation. And I look at this problem with z equal mu on the boundary. Okay. Now, for existence of solution, the existence of solution also is classical. We have obtained it with, I think it's with Marie-Françoise and Gwen. And of course, by the maximum principle, z is bigger than the Poisson potential of mu. Now, okay, but z is in LP rho. So this implies that this term is in LP rho. This implies that this term is in LP rho, and this implies that u mu is in LP rho. Okay, this is his conclusion. Okay. Now about the gradient, how to do with the gradient? We do to the gradient in the following sense. For the gradient, we look at the green potential of u mu to the p. This is a function which is in L1 row, so I can take the green potential, and phi is positive. And what I have minus summation of u mu plus phi is integral of grad u mu to the q. Now, so this is a u mu plus phi is a superharmonic function. We use now the Doob theorem, which says essentially that if we have this configuration, then the Laplacian here, which is taken at the sense of almost everywhere, belongs to L1 row. This implies that grad u mu belongs to LQ row. And the remaining of the proof is classical, is very easy. So we have seen the two terms important is we have that u mu is in LP row and grad u mu is in LQ row. So this is the scheme of the proof. Now, what is the link between those capacities? So we use a result in the book of Adams-Edberg, which essentially is a study relation between capacity. So the relation between capacities, it proves this type of estimate. The capacity of the Bessel capacity beta p is bounded by c times the capacity alpha a to some theta under some condition involving alpha p and beta. Okay. If there is no p here, it should be beta. Okay. Okay, and some theta. So now we assume we apply this result. What do we have? We have the following, that if p is bigger or equal to n plus 1 over n minus 1, and q is between 2p over p plus 1 and 2, so only the capacity corresponding to 2 minus q prime is needed. That means that the other capacity, the capacity C2 over pp prime, is bounded by this one to some power which is bigger or equal to 1. Okay. So in that sense, we have this result. Now we have also another result when q is between n plus 1 over n plus 1. The preceding was, the preceding was q is bigger than 2p over p plus 1. Now this one, is q is less than 2p over p plus 1. So in that case, the dominant term is the capacity C2 over pp prime. So only this estimate is needed in order to prove the result. Okay. And it's important that to have that with corollary 1, corollary 2, and the remark about in the case where the parameters P or Q are subcritical, that we can cover the full range of PQ is 1 infinity times 1, 2. That means in all cases, only one capacity is needed. Okay, now I'm just going to speak about a solution with separable solution. You know that this notion of separable solution, that means specific solution times 1 power of r times a function on depending only on the spherical parameter omega, plays a very important role in the description of singularity. So I look for this type of a solution of the equation when in that case I assume that my domain is a subdomain, of course, of the half space Rn plus, or in Rn too, but it needs, of course, some geometry of the domain. So first, the existence of such solution implies, first, we are in the range of the invariance of the equation respect to the scaling TL, that means Q is 2p over p plus 1. And in that case, the power alpha is 2 over p minus 1. And what is the equation which is satisfied by omega? So if my domain is a cone generated by a domain S over Sn minus 1, I have this equation, which I call it SPM of omega, in minus, this is the Laplace Beltrami operator, minus beta prime of omega, plus a parameter here, alpha times n minus 2 minus alpha of omega, plus omega p minus 1 omega, minus this term here. In that case, the exponent q become to p, because q is 2p over p minus 1, p plus 1, we have this one. So this equation. Now, what type of result we have this type of for this equation? If the equation is considered in the whole space Rn minus the origin, that means S is the whole sphere Sn minus 1. So positive solutions are unique and constant. The problem is completely solvable, and you will see it in the talk by Marie-Françoise, and she will speak, of course, of that because it plays an important role. Now, if for a boundary singularity problem, the model case is S is a upper hemisphere, Sn minus 1. That means that the domain omega, I replace it if I want to analyze the problem by Rn plus the half space. And the problem in that case is this one. I would like to study a little this one. SPM of omega is 0 on the upper hemisphere, and omega vanishing on the equator of the sphere. Yes. Now, if m equals 0, this is a result we have proved with Guimera, that there is no positive solution when p is bigger n plus 1 over n minus 1. So, of course, we are going to see what is the link between this threshold. The threshold will be important. Okay, so what we have the following. There exists a positive solution omega to the problem 133, this one. If one of the following conditions is satisfied, either 1 is less than p is n plus, and p is less than n plus 1 over n minus 1, and m is positive or 0, or p is n plus 1 over n minus 1, and m is strictly positive, or p is between 1 and 3, or p is bigger or equal to n plus 1 over n minus 1, and m is larger than some specific value here, mnp, or some explicit value, mnp, which depend on, okay. Now, the existence of this type of problem is obtained by constructing a super solution. For example, any large enough constant is a super solution, and sub-solution. And sub-solution, essentially, they are obtained in taking for delta small enough. We have that L, if phi1 is the first eigenfunction of the Laplace Beltrami operator on the upper hemisphere, then I have that S P mu of delta phi1 is less or equal to 0. Now, the result obtained in the last case, this one here, you see that non-existence of solution. This result actually is rather sharp. Because I know that if p is bigger to n plus 1 minus 1, and if m is less than or equal to m double star, there exists no positive solution to the problem. And again, the proof is based upon the transformation omega is eta to the b with b positive. This is an important role for non-existent. For proving non-existence, this is a very important transformation. Okay, now with in the case where p is, again, when p is between 1 and n plus 1 and minus 1, and q is less than n plus 1 over n, then we know that we can prove the result existence of solution with a Dirac mass on the boundary, any Dirac mass on the boundary. So actually, for k is bigger to 0, there exists a minimal fundamental solution which satisfies the equation LPQM is 0 in omega, which behave like this one on the boundary, which means exactly that it has a direct mass, k times the direct mass at the boundary. Okay, this is this solution. Now we can say, of course, when you have this type of solution, this is a minimal solution. What happens when k goes increase? This is increasing. K maps UK is increasing, and it increase, and we have a priori estimate. So there is a limit. Okay, there exists a limit, and actually, what happened? It does what is the role of the U infinity, and well, U infinity can be associated to two limit equations. One of them is an equation which corresponds to the Emden-Fowler type equation. That means that a separable solution of the Emden-Fowler equation. So this is this equation we have studied with Gmira. That means you look at minus Laplacian Beltrami plus alpha n minus 2 minus alpha psi plus psi p minus psi is 0 on the hemisphere, upper hemisphere, vanishing on the boundary. So we have with Mira, we prove that there exists existence and uniqueness of a positive solution when p is between 1 and plus 1 over n minus 1. Okay, that means m is 0 here, essentially. This is one of the limit possible equation. And actually, what we prove the following, that if p is between n plus 1 over n minus 1 and q is less than n plus 1 minus 1 and m is positive, so we have the following. If q is strictly less than 2p over p plus 1, then this is the Emden-Fowler equation which imposes its rate of blow-up. That means the U infinity function blow up exactly like R to the minus 2 over alpha. That means minus 2 over p minus 1 times psi. Psi is the solution which was corresponding to the Emden-Fowler equation. That means separable solution. Okay. And now if q is 2p over p plus 1, we have that the U infinity is behaves like the solution which approves we approve the existence. That means we approve the existence. In the case q is 2p over p minus 1, p plus 1, we approve the existence of a separable solution. And in that case, omega is the minimal solution of this spherical equation that we have defined before. Okay. This one. Okay, so well, I'm going just to say that there exists also this type of okay, so this one is yeah. Okay, now we have this to this point. Now this is a case where, remember, this is the case where q is less or equal to 2p over p plus 1. That means essentially in that case, this is okay. When q is less, strictly less than 2p over p plus 1, the Emden-Fowler equation is dominating. When q is equal to 2p over p plus 1, then in that case we know there is a mix. When q is larger than 2p over p plus 1, the blow-up rate is essentially modeled by the aconal equation. There is no diffusion. That means that the blow-up rate is going to be governed by this exponent, gamma equal q over p minus q. So it's an important fact that the aconal equation has a solution which is essentially isotropic, that means invariant by kind of rotation sense. And it's much more difficult to construct a solution vanishing on the boundary, except at one point. So we use a technique, a rather delicate technique of construction with sub and super, with sub and super solution, and we prove that if m is positive and p is bigger than 1 and q is bigger than 2p over p plus 1 and less than the minimum of 2 and p, then there exists a positive solution of the equation LPQM is 0 in Rn plus, which vanish on the boundary except one point, and which satisfies this type of equation here, this type of estimate. That means it's bigger than r to the minus gamma times phi 1, while this is going to be the sub-solution, and is dominating by max of r to the minus alpha and m times 1 over p minus q r to the minus gamma. So this does not show, of course, that the solution vanishes on the boundary. Okay, but the solution what we construct vanishes actually on the boundary, but we don't know exactly how. Okay, and so this is valid. Not this type of estimate is not valid for all r, but that means essentially in the domain 0 times r star times Sn minus 1 plus for some r star. And now I know, of course, this is something which is up to now we have obtained, but it's not probably optimal, that if nq is bigger than n minus 1p, then r star is infinite. Okay, this can be probably, this can be adapted in a bounded domain, but technically it's rather difficult. Okay, this problem, I'm going to open a few problems. I think Marie-Françoise will speak of this. Now, in the case where we look at equation in all Rn, we can prove the existence with as a rate of blow-up corresponding to the Riccati equation. This is a rate of blow-up of Riccati equation. That means it is possible to construct in Rn minus 0 solution which satisfies this type of blow-up. U of R is psi to the mr to the minus beta 1 plus little o of 1 as R goes to 0. For some specific value psi n. Okay, this solution, the blow-up at a blow-up rate which is smaller than the one of the explicit radial separable solution. We don't know if there exists solution in Rn plus, which vanish on one point, with this rate of blow-up. Up to now, we have not proved it. This is the first problem. Okay. Second problem is it possible to define a boundary trace for positive solution? Okay, this is not easy, but it's important to notice that it holds for the Emden-Fowler equation. This all the works that we have done, that I've done with Moshe, and also for the Riccati equation minus Laplacian of u equal u positive equal grad u to the q. This is just Doob theorem. Essentially, it proves that the boundary trace is a random measure. Okay, and the same, of course, is it could be equivalent to define a initial trace for solution of the associated parabolic equation. Well, there is a problem now of uniqueness, and okay, for the Dirichlet problem with measured data, it's not clear what are the results for uniqueness. We have a few results on uniqueness for solution with a boundary isolated singularities by using essentially scaling technique, but with some geometric restriction at the moment. Okay, now a similar analysis for boundary behavior is this type of equation. Look at this one. I call it is called Serin's equation. The operator now becomes minus Laplacian of u minus u to the p plus m grad u to the q. Okay, so this is a work that I've done a little with Marie-Françoise, and what we get essentially a priori estimate. It's more complicated, of course, you see here, because it's going to be a forcing term. So we have the limitation with Sobolev exponent when p is bigger than plus 2 and minus 2. And the solution with boundary measured data, this is exactly the same technique and the same result. It's great. This is the same method. because we have a subsolution, super solution, we can do the same. And okay, the solution with isolated boundary singularity, we have a few results by method of super and subsolution. And the boundary trace, it's fairly understood. Okay, so we have some result like that. Okay,